Looks like there's still a few people connecting, but we'll go ahead and get this thing kicked off. Thank you for joining us this morning. My name's Jeremy Morton. I'm with TechStar. We're doing this video conference today from our office here in Deer Park, Texas, and we appreciate you guys taking the time to join us. We've recently partnered with the vibration guys for vibration analysis type services. And we've been really excited about making this announcement. Unfortunately, COVID has kind of slowed things up a bit for us. But anyway, with that being said, we're going to get things kicked off. There's a 20-second delay between the camera and what you see. So just keep that in mind. But please, throughout the presentation this morning, feel free to ask questions. There's a little sidebar there next to the screen. You probably already see us communicating there. Please feel free to ask any questions that come to mind there. Jack and I will do our best to make sure we address those questions. And with that being said, we'll get things kicked off, and I'll hand the things over to Mr. Staudt here.
Hello, everyone. My name's Jack Staudt. I'm with the Vibration Guys, LLC. Like Jeremy was talking about, we've business partners together, and going to help them out on services for vibration analysis and any other type of condition monitoring services that you may need. Today we're going to talk about the basic vibration analysis. That's your first step of reliability. Other tools that in the near future we're going to talk about is ultrasound, thermal imaging, motion amplification, oil analysis, and also the training that you can get here at this facility that we're going to be offering here real soon. So to get started, we're going to just basically talk about the basic vibration analysis. Some of you advanced people, it may be a little boring to you, but please bear witness with us while we get things going. We're going to have interact, even though we're talking about basic vibration. If you have any other questions, maybe advanced questions, we're here to answer them. So to get started with our slide presentation, and I hope everybody can see the slide presentation, we're going to talk about the objectives of what we're going to cover. I guess we're waiting on the 20-second delay.
Yeah, so
there
we go off of your screen, and then that screen will be 20 seconds.
Okay, all right. Yeah, I'm all new to this, so that's what I'm like. But thanks for bearing with us.
Yeah.
So we're going to define vibration. What is it? Where does it come from? Describe measurements, methods. Discuss time and frequency. The difference between the time domain and the frequency domain, relationships between the two, examine amplitude measurements, the differences between the three, choose proper transducers, right probe for the right application. So how do we define vibration? Movement of a body about a reference, response to some form of excitation, pretty much like the song you hear from the Beach Boys. Forcing functions, several types of methods of vibration that you can find. You have what's forcing frequencies, and then you also have system vibration. We're going to try to discuss a little bit of that. But sources are imbalance, misalignment, belts, gears, bearings, rolling element, and sleeve bearings. Looseness, electrical anomalies, instability of the oil. Looking at resonance. So little introduction. We look at vibration where it moves left to right. Our amplitude is our y-axis, our frequency is our x-axis. just another little key note, if you're looking at Bentley Nevada instruments, this is also how the probe orientation is too, where you have your Y probe and your X probe. A lot of people never knew this about Bentley Nevada systems, but no matter how you look at your probe, this is always going to be your Y probe, this is going to be your X probe, no matter how you look at it. And you're looking from the driver to the driven. Yeah. So the motor to the pump.
And that can get a little confusing when you're going through a gearbox or anything, but as long as you always keep the driver at your back and the equipment that's being driven to your front, that Absolutely. X and Y always holds true.
Absolutely. Unless somebody's gone in there and switched a few wires.
Yeah, I know early on when it's a 45 left and right and you're thinking horizontal and vertical, it can kind of throw you off. Or if they're underneath, on the bottom half of the bearing for whatever reason, that can throw off a lot of people. So
Absolutely.
That's a good point.
Yeah. We start off by looking at time, the time domain. How does it work? In the relationship of the rotation of a machine, we take the time domain and we want to convert it to a frequency domain, and we use what's called FFT, fast Fourier transform, algorithm that computes the discrete Fourier transform of a sequence or its inverse. Fourier analysis converts a signal from its original domain to a representation in the frequency domain and vice versa. This was all discovered by French mathematician Jean-Baptiste Joseph Fourier back in the 1700s.
And I think one of the important aspects here, this is ultimately what we're trying to gather from the vibration data. If you go with a 4 to 20 milliamp transmitter, all of this is basically null and void. You may get an overall vibration amplitude, but all of this rich data that you're getting, the FFTs, all that, you basically lose all that.
Right.
So you may be able to catch a trending upward vibration signal, but that's about the best you'll be able to do.
That's
you can't tell what's causing it between all the failures that you listed earlier.
Yes, yes. So we look at our time domain, and we use FFT to convert it to frequency domain. And a very complex waveform could tell you a lot of things that's happening with that machine. Back in the old days, we had to use oscilloscopes to do this, analog oscilloscopes, and we didn't have the ability to use a FFT. Nowadays, coming back from what it was like in the 80s, we have instantly information that's at our fingertips to understand what machines are doing.
Yeah.
So the mystery of vibration analysis using an FFT, we take the time domain and we convert it to frequency domain. And we come up with our spectrum, which gives us frequency and amplitude. If we have our amplitude and our frequency, we can pretty much diagnose what's wrong with machines. RPM plays a big part of this. You have to know what your RPM is of the machine, so you can see if your frequencies all line up to the rotational speed.
I guess an important point too, this is a half spectrum that you see there on your screen. Sorry, I may have lost you guys. Let's see here. What just happened? It closed. All right, there we go. That's a half spectrum that you see. So basically that's all your forward precession vibration. You'll also hear there's a full spectrum, and you'll have from where basically on your x-axis there where it's 0, you'll have negative frequency components as well that can be different sorts of machinery failure and things like that cause those. But just for your own reference, so make you aware of it.
And we're going to cover some of that. That's all. So we're going to talk about amplitude. There's 3 ways to display amplitude. All 3 show severity. some better than others. Displacement is distance a body moves, point A to point B. Velocity measures the speed, time from point A to point B, and rate of displacement. And acceleration is total forcing acting and change of direction. I had a customer one time. He had his very cheap vibration meter mounted on his fan. About every 2 months, his fan would become unbalanced because of buildup on it. It was at an asphalt plant, and he would put a half bottle of water on top of the panel next to the fan, and when he would start seeing waves in the bottled water, he said it was time to call me to come out and field balance the fan. So that's what displacement is measuring, is the top of the wave to the bottom of the wave. So that's that was his 99-cent vibration analyzer. We look at displacement between correlation with the acceleration and velocity. Displacement measures low frequency better than it measures high frequency. Acceleration measures high frequency better than any low frequency. And velocity measures across the frequency span pretty equally, but not as accurate and resolution. But the velocity is why we would use that as a walk-around vibration program, because we can identify low frequency and high frequency at the same time, and then go back with our analysis. And if we have to really, look through the data with a microscope, we can change things to displacement or acceleration, whether it's unbalanced or even subsynchronous type frequencies, or we're looking at gear mesh frequencies with sidebands. We'd want to probably look at acceleration.
So velocity is it's kind of that middle ground. You can cover some of the displacement applications. You can cover some of the acceleration applications.
Absolutely.
And if, like you said, if you're on a gear mesh type application, obviously you'd probably use an accelerometer for more in-depth analysis on those higher frequency applications.
That's correct.
Gotcha.
Yeah. All right. So amplitude, like we said, there's 3 ways. We look at displacement. We here in the U.S. we use mils, peak to peak. Velocity is inches per second peaks. Some places like RMS, and then acceleration we measure in G's, RMS here. But the question always comes up: is there a difference between RMS or peak velocity? And the only difference is the standard that's out, the ISO standard. You just have to remember that your RMS and peak has different distances from the wave, and we're measuring like RMS is 0.707 from peak, where peak is 1.414 from RMS.
So in your opinion, are you losing any critical data when you go to an RMS measurement versus a true peak measurement?
No.
No? Okay.
So, then we look at acceleration. Acceleration, back in the old days, we used to measure at 0 to peak, and we've kind of got a standard going here in the U.S. that we're measuring RMS. We look at our transducer location according to ISO recommendations, and also we look at our amplitudes, and we try to base everything off ISO, on the different size of the machines that we have the capability of doing. I don't think we're moving too fast.
Yeah, it's that's the delay that we're seeing here on the screen in front of us. So, but yeah, I would say just we're still connected. Everything looks to be. It's just
okay.
a delay in their system. We'll see. Seems a little longer than 20 seconds.
Yeah, it is. It's all right.
Guys, can y'all confirm that you can still hear us clearly? We just want to make sure, because our screens aren't really updating here even after the 20-second delay. So it's going to take you 20 seconds before you hear that.
Yeah.
Yeah, maybe go forward to back.
Well, yeah.
I don't know.
That was
Okay.
several slides ago.
Yeah, they hear us good.
Okay.
What is RMS was a question that came up. So it looks like the slides aren't updating for you guys, maybe what's going on right now.
Yeah.
So
RMS is root mean square.
root mean square, there you go. And typically to calculate RMS, you take a peak signal and you multiply it times 0.707. There you go. Looks like is your screen share? Yeah, still sharing.
Yeah.
I think so. It sounds like the audio is coming through good for you guys, but for some reason we're having some technical difficulties here on the presentation. It looks like the presentation is not updating possibly. So give me just a moment here, guys. So Jack, while they're working on getting this to update,
Yes.
Tell us a little about the Vibration Guide, who you are, and kind of give us a little background on the services you guys provide.
Sure. Actually started business in 1996. I had worked for a lot of the big name companies here in the Houston area. And my wife calls me up one day and says, "Hey, you ought to start your own business." I was like 39 years old, and everybody that was in business at the time was all over 50 and or maybe older and didn't have hair. And I said, that kind of scares me, gray hair and no hair. And she says, "Well, you'll get there." Well, here I am.
Well, instead of turning gray, it turned loose, I guess.
That's right. But started out, it was just me at the beginning. And I started hiring a few people off and on and built this business up for the last 22 years, I would say. And we go, around the clock around the world. We don't have no in our vocabulary.
So are you guys doing more connecting to remote systems now and doing diagnostics remotely? Are you seeing more of that now?
Yes, yeah, that's I was involved in wireless vibration in 2008.
Oh, well.
And you could tell it was, a lot of people were trying to throw the wireless system out then, but there was like 20 to 30-minute delay, because we just didn't have the speed of the internet and cellular and then also memory. We had memory problems too, where were you going to store your memory? So I told them back then that it was just not ready for wireless at the time. And now such improvement in storage and speed, and it makes more sense now for the wireless systems that are out there. There's probably in the last 5 years, we went from probably about 12 wireless systems to several hundred now. It's like every day somebody's calling up and say, "Hey, try our wireless system."
Sure. The industry is definitely evolving with the technology.
Oh, yeah. Yeah, it's a lot of it. And they have several types of the wireless system. You can have what I call the no-go,
red light, green light.
That's it. Yeah. You can get that. Or you can get out where you have full analysis like you use on your walk around. You can't, you can do reports, but like your go, no-go is probably your low end of the cost. Where when you're using the analysis side, being able to analyze spectrums and everything right in the comfort of your own house.
Oh, nice.
So that's a little bit more expensive to have.
Sure.
Then there's problems that do you use cellular so you can kind of bypass some IT issues. We always have IT issues in the plant, because
They're all
Wi-Fi or Cat5 or whatever you're trying to run, right? So there's still a lot of issues there, and that we have to address some way or somehow, in the future here, how to move forward with the wires.
Sure. As battery technology improves, as our infrastructure with networking improves, I think we'll see a lot of changes. So.
Yes.
Well, good deal. It looks like I think our screens are back in sync here, guys. So,
all right.
We'll move back to the presentation. Sorry for that.
Yeah. All right. So we're talking about transducer location. We want to do our XY, horizontal, vertical, and an axial. We also we use the. I was talking about the chart you might see. Let me back up on that, where we can see the standards, the ISO standards of the color charts, and the what amplitudes are green, yellow, red. Also based off of different types of machines with either flexible foundation or more of a really tight foundation. So we're going to get into some of the terms. If you're new to vibration analysis, some of this may not make much sense to you, but we talk about phase, the relationship between events relative to a reference. A lot of people ask me what is phase, and I said if you get two people in a boat rocking together, you're in phase. If they rock opposite from each other, you're out of phase. So that's kind of like what your machine does too.
Sure.
And you can measure this with the right analyzer, data collector. So many of them out on the market. You have two ways you can use what's called absolute phase analysis. That's where you'll use a transducer and a tachometer, and then you can do two-channel relative phase analysis. And that's where you use one channel as your reference and the other channel as your movable.
Okay.
The term amplitude, measurement of energy of a vibrating object. Displacement, distance a body travels. Units are peak to peak. Velocity, rate of which displacement occurs. Units, inches per second, peak, or millimeter second RMS. Acceleration, rate of change of velocity, and units, G's and RMS. Pretty much how we measure displacement, we're measuring the displacement from one peak of the wave to the bottom of the wave. Velocity would be, imagine that you're on the freeway driving at one constant speed. That's measuring velocity is measuring from 0 to peak, what the speed would be to get to that. And then acceleration would be like if you were going onto an on-ramp and you're measuring how fast it takes to get to the
0
velocity.
to 60 or
Yeah, so that's pretty much, just kind of in terms to try to identify how that is measured.
There was one question that came up, and that you may be addressing this later in your presentation, but it was asking about triaxial monitors that go to your phone, pros and cons. So it mentioned XYZ 5 monitors, but basically a triaxial sensor, the pros and cons of triaxial.
Yeah, and probably talking about using some sort of app that will monitor a triaxial. And That's what I would say a cheaper way to be able to monitor. The accuracy, probably within 10%, and being able to see all X, Y, and Z at the same time. That really depends on what type of accelerometer you're using. If you're using a MEMS or you're using a ICP type accelerometer too.
Oh, so that makes a difference.
Yeah.
I guess and I'm not from the diagnostic world like you are, but I guess that was always a question I had is, a single sensor mounted in one plane. A lot of times it's in the vertical plane.
Mm-hmm.
How effective is that one sensor at measuring a horizontal vibration or an axial vibration from that single plane?
Yeah.
In your opinion, do you get good quality data? Are you able to make diagnostic calls based off of that?
Yes, you can.
You can? Okay.
Yeah. I prefer, personally myself, I like to collect data in line with the shaft.
Sure.
And collect it at the bearing locations because that's the stiffest part of the machine. So you're going to get like true readings right there. But the triaxials, even if you're like setting it on top of the machine and you're getting an inline of your vertical, but maybe not your horizontal, if you're consistent with it, it works well.
Okay. And I mean, a lot of times there's cost considerations of drilling and tapping and installing these sensors, running additional wiring, things like that. And so it's not really cost effective to put a sensor in each individual plane. So I guess in those cases where you can't really justify the cost of doing that, a triaxial sensor it gives you data that's good enough to work with.
Absolutely.
Yeah. That's good enough.
Yeah. So we'll move on to the other terms. We're going to talk about frequency, how often an event occurs per unit time. Units we look at as CPS or cycles per second, or in our world we call hertz. Cycles per minute, CPM, and RPM, revolutions per minute, are pretty is similar, are pretty much the same. And then we have orders, which are multiple of turning speed frequencies. So we have in our world, we have different ways as we're monitoring the different frequencies that you have people that like to use hertz, and then you have people that like to use CPMs, and a lot of people will ask the questions, is there any difference between the two? And there's not, You just have to understand if you're in hertz and you want to try to see what the relationship is to RPM, it's 60 times the hertz frequency to come out with what cycles per minute is, and vice versa. Divide 60 in that to see what the hertz is.
Whatever you're most comfortable with looking at.
That's right.
But when you're doing your diagnostics, it's important you understand what data you're looking at, if it's in CPM or if it's in hertz.
Absolutely, yeah. And a lot of guys that I train, they come from the mechanical background, so they understand the RPM.
Yeah.
So I try to train them with using cycles per minute, so they can understand that hey, that's.
You get a guy with electrical background; he's more comfortable dealing in the world of hertz. So,
yeah, that's absolutely sense. Yeah. So that's how I try to train people what they're most comfortable with.
Sure.
And we'll talk about an effective program. You have to choose the proper transducer for what you're doing. You're wanting to monitor gear mesh. A proximity probe may not be something you want to use, for analysis. Signal processing, your time waveform and your spectrum. What type of problems are you going to do? You got to examine all the data that different sets that you get and everything. Understand, And then the always question is there a true problem? Get called out a lot of times, and may travel for 5 days to get there in 5 minutes, so you don't really have a problem, and that happens a lot. And so it's you know, and I'm talking about mechanical problems. It
Sure.
may be something more on piping or something like that.
Noise induced into the vibration
Absolutely.
signal, things like
Yeah.
that. Yeah, and that's a big one. You know, I mean, we spend a lot of time talking about condition monitoring software, and a lot of people invest a lot of time, a lot of money into these really high-end, very capable systems. But that software is only as good as the data that it's being fed.
Absolutely.
And if you use the wrong sensor in the wrong application, or your sensor is not set up correctly, not verified, maybe it's not functioning within spec, that data that you're looking at in that CMS system is going to be jeopardized.
That's right. That's right. Yep. So we look at our diagnostics, how we're going to do it. What is the source of the vibration? You know, that's pretty much the starting point of any analysis. And then afterwards, you want to do root cause. You know, is this going to fail again like this? I had a steam turbine one time that had a locating bearing. It's a rolling element bearing. It was probably, I think they told me it was a $50 bearing. And every 18 days it would fail.
Oh, wow.
And, you know, and we'd pull it, cut it apart, and we'd look at it, and it, you know, it just had all types of divots all in the outer race. And it really had not a load on it. It was just more for locating the shaft.
Wow.
So we did some testing on it, and we found out that it had electric current going through it, and was able to diagnose that, hey, they just had an outage and they didn't attach the ground wire back to it.
That'll do it.
And once they did that, then
So you're getting arcing basically, and it was causing a defect in the outer race. Wow.
Yeah. So we you know, taking your bearing, cutting it in half, trying to identify what the problem was. And really how we found out, we cut it in half, and I had it sitting on my desk, and I flipped them back to back, and they magnetized together. Wow. And I was like, okay, well, there's the problem.
Yeah.
You know, so.
That's interesting.
Yeah. So it always pays to do the proper root cause.
And Charles mentioned, you know, orifice plates. Yeah, they can induce a lot of noise, and that's specific. That's a good point, Charles. So case-mounted sensors, accelerometers, velometers, old seismo probes, things like that. They definitely are more affected by outside vibration sources. Yeah. So if it's an orifice plate, or you know, that's you're getting a lot of noise from, or maybe piping or something, getting wires flapping in the wind, compared to a displacement or proximity probe that's actually mounted to the bearing and looking at the rotor itself. Those are much less susceptible to outside noise influences like that.
That's correct. Yeah, case mounting, you could pick up anything.
Yeah, and that's something you want to consider when you're installing these sensors on a machine permanently. You know, where you're mounting them. You know, are they going to be used as a step for someone to climb up on to get to an instrument up above?
Absolutely.
I've seen many of them snapped off laying there with a cable attached to them. So.
Yeah, I just a couple of weeks ago, I was at a location that they were monitoring in the axial position on a gearbox. And it was like right in the middle of the gearbox, and the vibration was high because it was giving the stereo effect, and there was no support there.
Yeah.
So if you went off to the corners, you had normal vibration, but there it was amplified by 3 times.
Yeah, you're getting that flex of the gearbox casing instead of directly over where the bearings were,
and
more rigid.
Gearbox had proximity probes on it, and you know, monitoring the shaft, there was no issues.
Zero problems.
Yeah. So they were all concerned about that one point right there, and you know, I was like, don't measure there.
Yeah.
So
installation is key on these systems.
Right. So we'll review a little bit about the amplitude, look at acceleration in G's, velocity in inches per second, displacement in mils. Our frequency, cycles per minute, CPMs, cycles per second, hertz, CPS, revolutions per minute, RPM, orders, frequency, turning speed, just some of the terminology that you'll hear out in the vibration world.
Sure.
RPM versus cycles per minute. A lot of people talk, you know, ask questions about that, you know, is what's the difference between? There's no difference.
Yeah, just 2 words.
That's right.
Mm-hmm.
You know. So we'll talk a little bit about transducers, convert mechanical signal to electrical. 3 basic types. And if you ever notice right here in vibration analysis, there's always 3.
Yeah.
You know, if somebody asks you how many ways you can do this, the answer is 3.
Always 3.
Always.
So just remember, if you don't take nothing else, there's always 3. So
that's right. So displacement transducers, velocity transducers, and accelerometers. We look at a displacement transducer. It's actually measuring, using eddy current, the motion of the shaft, linear motion of it. So, you know, for this system to work properly, you've got to have everything perfect.
Yeah. And that's a good point. You know, when we say the shaft, typically these systems come off the shelf calibrated for 4140 steel.
Mm-hmm.
If your shaft has a chrome coating, or you're looking at tungsten carbide, or you're looking at a different shaft type material,
Mm-hmm.
you need to make sure you specify that on the front end of putting one of these systems in.
Absolutely. We ran into that problem one time on a 10,000 horsepower motor.
Yeah.
It had failed, sent it to the shop, and they said, hey, we did you a favor. We chromed the journal area for you. We were like, thanks.
Yeah. Surely they roughed up the surface before they put the chrome on there. So yeah, that's a common issue that we've run across.
That's right. And I've had this question asked that from different customers. They will call me and they'll say, we just received our shaft and there's a piece of green tape. Well, if you're using like proximity probes, usually where that green tape is the probe area.
Yeah.
And that probe area is burnished, and I mean it's perfectly smooth right there. They try to take out all the scratches. If you have a scratch in that area, your probe is going to look at that when your machine is running, and it's going to help amplify your amplitude.
You just created you a keyway for a phase reference.
That's right.
But yeah, I've seen people take a knife and cut that tape off.
Absolutely.
You've got a clean knife stroke across that burnished area.
Yeah, you don't want to use that.
Don't do that.
Yeah, that's correct. So advantages of using a displacement transducer: measures relative movement, good for sleeve bearing machines, very good for heavy machines. Disadvantages is that it's permanently installed, you know, and like I say, it's got to be perfect. It's got to be perfect in there. You know, you run into issues where your probe may be getting it data from the housing itself because it's not set far enough.
Sure.
And you have to have your gap voltage set just perfectly too for your curve to make sure you're not running off your curve if you have any type of thermal growth or anything like that. So
it's a much more intrusive installation.
Yes.
Typically you have to drill and tap if your machine isn't modified into the bearing caps and through the housings.
And that's some of your background, isn't it?
Absolutely. That's where we come from. So but yeah, we can certainly, you know, we do that daily.
Yeah.
But you know, it has to be the right application, you know, for that sensor.
Absolutely.
You got to look at the cost of impact of that machine if it goes down and justify, is it worth the expense of putting a system like that in?
That's right. I mean, the driver, you know, the transmitter, you know, you have all this that could have some type of issue with it. And, you know, I get called a lot of times to come out because they're having some type of issue. Just for instance, this one machine, they set the probes at the factory, but they set it for the machine to be, you know, shipped there. So there's no, so they back them out.
Yeah, they back them out so there's no contact.
But they're still within the gap range, but the gap range may be like negative 17 volts or something like that. You know, you're right on the very edge of the curve. And then they install the machine and run it, and then they start having vibration issues, and they don't understand. And then you go there and you find out they never field adjusted.
Oh,
once it was installed. So,
I've seen that,
yeah. So
and I've seen the opposite end of that, where they made contact during shipping and damaged probe tips as well. So.
That's too, and scratch the burnish area.
Yeah.
And people always ask me, can we burnish the area while it's rotors in the machine? And I go, I've been wanting to figure out how to do that. Boy, if I could patent that and get that done, that would be great.
So it's got to go in those V blocks back at the shop.
That's right. You know, another disadvantage is we only go out to 1 kilohertz. Some of the newer probes go out a little bit further, but back in the day, DC to 1 kilohertz for your accuracy. So your, for your CPM guys, that's 60,000 cycles per minute.
Yeah. But in the world of heavy, rotors, large sleeve bearing type applications, is there any frequency components beyond that 1 kHz that you could do diagnostics on a machine like that? They come to mind.
Yeah, most machines, probably 98% of the machines, you're in the range, but you may have like prox probes on a gas turbine that's turning 20,000.
Okay. RPM, so higher speed.
Yeah. So
sleeve bearing application.
By doing that, you're able to get about 3 times the frequency, turning speed frequency to analyze. Gearboxes, a lot of people may have a high speed gearbox where, your output speed's 12,000. Just like your input speed could be 20,000.
Sure.
From a gas turbine. So there's a little bit of variation there, but just like gearboxes, I always say, even though you have Bentley Nevada mounted on your gearbox, prox probes and everything, also take case readings.
Yeah. Yeah, typically best practice on that is to have your prox probes on the sleeve bearings and then have an accelerometer installed for your gear mesh frequencies and things. So.
Where your prox probes work the best is on machines that the rotor weighs 4 times less than the case.
Gotcha.
So you have like this big heavy case and it's real thick between the bearing and the outside. And this rotor inside is really light. So if you take a case reading on it, and you look at like these centrifugal compressors, boiler feed water pumps, some of these big boiler feed water pumps, the data you're going to collect is going to be very accurate because you may have to go through that much steel to transfer through to get that reading there.
Sure.
So that's why prox probes are great on low speed machines too.
Yeah.
So that's some of the advantage with that. And power is required when you're using this. So if you have any type of glitch in the power system or that, then you lose what you're doing with it. Sure. We have velocity transducers. Don't really see a lot of them out there like we used to.
More like recips, lower frequency type impact applications, things like that. You see a lot.
Well, we're seeing velometers.
Yeah, velometer.
Yeah, we're seeing more velometers. It's accelerometer that has circuitry inside it converted to velocity.
Integrated acceleration, you do velocity. But you're doing it there at the sensor versus doing it at the monitor and integrating noise.
That's correct. So. Yeah. So you have different sensitivities.
Sure.
And that pays if you're like somebody new coming to a system, if you don't know the information, then your data is going to be wrong.
Yeah. So, makes sense.
But the old velocity transducers like you used to see mainly on gas turbines and things like that.
So this is what we often call like a seismoprobe. It's actually a mass in a spring, and you can hear them rattling around in there.
And you don't have to power it.
Yeah, and they're sensitive to where they're mounted. Right. There's a certain angular degrees on them typically. It tells you where it can be mounted.
That's right. So, best signal to severity ratio and also good signal noise ratio, but no power required. That's the advantage of it.
Yep, self-power.
A single integration that is needed, so let's say if you're going to convert it to displacement, so you only have to, it's single integration, and then if you're, you can't go back with it for acceleration. So
yeah, the only time I've really come across those myself is in older power plants, some of the old boiler feed water pumps, and some of the large steam turbine generators. I've seen a few still out there, but not very often.
Yeah, and some people used to use these as their walk around too.
Oh, okay.
So if you've ever held one, it feels like it weighs 5 pounds.
Oh, sure.
So the vibration guys back in the early days, they looked like they worked out because they had to carry this big old probe around. So the disadvantages is, like I said, they're usually big. heavy. They go out to 2 kilohertz, 120,000 cycles per minute.
Okay.
So again, if you're looking for gear mesh and maybe 3 times gear mesh, this would not be the probe you'd want to use. Okay. Temperature sensitive, you know, because thermal expansion in the unit itself would change the calibration. And they're very expensive, you know, $2,500 for one compared to $99 for an accelerometer.
Yeah.
You know, just roughly throwing it out there,
Sure.
you know, what you can get for price-wise. Magnetic field sensitivity to it, and orientation sensitive. So like your horizontal, you'd get a sag between the springs.
Sure.
Wear and temperature change, it knocks the calibration of it out. So then we come to accelerometers. Basically what everybody uses for their walk around. Mm-hmm. If you've got some type of vibration program, more than likely you have a general purpose accelerometer. And that's the other thing. Accelerometers come in several different models. You got high frequency, you have low frequency, you've got general purpose. So you can get an accelerometer that goes that has a rating to 8 cycles per minute. So and then you can get one that goes out there to 2.5 million cycles per minute. So
and a lot of that's due to the application. A lot of your walk-around program is typically smaller, more balance of plant type machines, a lot of rolling element bearings.
Right.
So you're looking at those higher frequency applications of, you know, the rolling element, ball fast frequencies. Things like that.
Good, hardy, general purpose accelerometer normally costs you somewhere around $200 to $300, something like that. Yeah. Has an accuracy of 5%, you know, and these are very more trustworthy than the ones that are accurate to 15%.
Sure.
You know, and it's cost. You know, the 15% is going to be cheaper.
Sure.
You know, general purpose where the cable exit is top exit. Mm-hmm. You can get to about 900,000 cycles per minute. Wow. That should cover everything you need to do in most of the machine world. If you use a side exit will only go out to about 700,000. Okay. So there's a difference in Fmax, frequency.
I didn't realize there was a change there when you bring the cable out the side versus vertically. Now, from your experience, does the 5% tolerance versus a 10% tolerance, I mean, you're trying to do precise diagnostics, looking at the spectrums and things like that. Does that make a big difference in your world?
Not really. If you're consistent on where you're collecting the data,
okay,
then the $99 probe works fine.
As long as it's working and getting good, clean data, you can work with that. Okay.
Yeah. And then there's other types of probes you might consider if you're going to use, let's say, enveloping or peak view, spike energy. They have what's called more of an ultrasound probe that you can also use. A little more defined on the higher frequencies.
Okay.
So just come out with those. Then we look at the advantages. So like we were talking about, we have a broad frequency range. They're small, they're light, they're rugged. I've dropped an accelerometer off a 4-story cooling tower before and went back, calibrated, worked fine. Then I've had one roll off my desk onto the carpet and break it.
Yeah.
So
there's another consideration on those is the installation, how hard you torque them down.
Awesome.
You know, they have very specific torque ratings, mm-hmm. and you don't want to just get down there and crank those things down because it's a preloaded piezoelectric crystal typically, mm-hmm. and the majority of them, and you can very easily crack those crystals. It may come in okay on your monitoring system, but it likely will throw off the vibration readings you're getting. It can either cause spikes or it can cause where you're basically reading a zero flat line. So
absolutely.
You just don't know which direction it's going to go.
That's right. Yep, for sure. One of the other things I want to talk about on accelerometers, if you do have one go bad, throw it away.
Don't mess with it.
There's no way of repairing.
Sure.
So I've walked in places where they have 5-gallon buckets of broke accelerometers, and I go, "What are y'all going to do with those?" And they go, "We haven't decided."
Well, to be fair, I don't know of anyone that actually repairs the accelerometers under warranty if you send them back.
Well,
typically, you get a new one sent to you if it's under warranty.
Well, yeah, there's all these different companies now have lifetime warranty on some of
it's a good
their
point.
accelerometers. So, back in the old days, we did, so you had your bucket full.
Sure.
Accelerometer ICP needs no signal conditioner. So when we talk about ICP, it means your analyzer is going to power it up.
Okay. So it requires a loop power kind of to power the sensor before you can start reading.
Yeah.
Is there a difference in settling time on the ICP versus a?
Yes, there is. The ICP usually needs about 4 seconds to settle.
Okay.
We have different analyzers out there, different makes, models, that some of them will have the power start when you push the enter button to collect your data.
Okay.
So when you hit enter, you have to wait 4 seconds for it to settle down. And then there's other analyzers out there, when you turn the analyzer on, it's already powering the accelerometer. So you don't have to have that settling time. Now, if you jar it, you have to do it, and you get what we call the ski slope on the data. And also, if you're trending the data, you're going to have some type of wild anomaly look in your trend data too.
Is that typically the magnet on the bottom of the Excel? The guy hits record data and puts it on the bearing, and it
boom,
hits, impacts it, and so you got to wait for that to settle out before.
Right.
Okay.
Sense. And that's on the ones that's powered up when you turn the analyzer.
Okay.
Because it's already powered. Also, what you'll see is what I call a power jar. When you plug into, let's say you have some remote accelerometers, like let's say on a gearbox and a cooling tower, and you plug into it, and you still have to have that settling time for it.
Okay. Makes sense. Yeah.
So yeah, and they're easy to mount. Disadvantages, we say for as a handheld, that's just kind of my preference on it.
Mm-hmm.
Limited signal to noise ratio, reads acceleration, so everything has to be
or inches per second sometimes you'll see.
Yeah, that's right. So you have to convert to velocity or displacement depending on what you're doing, because you have integration one time to velocity, double integration to displacement. And you do lose a little value to your data that you're collecting by doing that. But if you're consistent, you base it off your consistency and of your data, and your information should be.
So when we talk about a velometer or accelerometer, they're very similar in how they're built and designed and everything. With basically the main difference being the accelerometer has an integrator circuit that's built onto the accelerometer.
That's what it is. Pay attention to when you pull one out of the drawer, because you don't know if you've got a velometer or an accelerometer. Most of the
they look identical when you hold them.
That's right, and they'll have their model number. Like I'll just give a shout out to Wilcoxon out there. They have their 793, and then they may have their 793V.
Oh, so that's their velometer version.
That's right.
Yeah, there's something to keep in mind.
Yeah. Like I said, double integration needed. So we talk about signal processing, the 4 primary types of signaling. We have our time domain, which is our waveform. We use our overall level criteria, selective frequency sweep filters. In other words, we go in and we say we just want to look at the one-time vibration. Mm-hmm. So we filter out everything else. And you learn more about filters if you're going into you touch base a little bit in a Category 1 training class. Category 2, you learn how you use the different filters. You have a high pass, low pass,
getting more into the diagnostic side of things
Yes.
versus the proper collection.
And band filters, yeah.
Sure.
So that, and all this can be trends, so that kind of helps you with your diagnostics.
Okay.
Frequency domain. So we look at frequency signature as an XY plot. X represents the frequency, Y represents the amplitude or magnitude of the signal. The data is divided into how many categories?
You guess three?
Three.
Okay. Lucky.
We have synchronous, which is a integer of turning speed.
Okay.
So,
and you have to have a phase reference to get the synchronous data, correct? Like a key phaser or a pulse per revolution?
yes, if you had some type, that would help, but you have to definitely know what the RPM of the machine is.
Gotcha.
Some of the analyzers that are out there, when you collect the data, you can actually locate the 1x peak in the spectrum and label it as the RPM.
Oh, so that's your reference point.
Yeah,
Okay,
so
makes sense.
you can set your reference by doing that.
So it's more of an inferred measurement, though. It's not really a measured variable at that
Right.
point. So
Yeah, and a little variation there sometimes, but,
Sure.
but yeah, that's and again, if you don't have the correct RPM of the machine of the where you're taking the data, let's say because we have variable speed machines now with the VHDs.
yeah,
What is
VFDs.
it? Or what is it? Variable drives.
Variable frequency
Yeah,
drives, yeah.
VFDs.
Mhm.
VFDs, yeah. Because of them, you know, maybe you have a machine that normally runs about 3,500, and now today it's running 2,800. You know, so you can't just have a fixed RPM set for that. You have to actually, when you do your diagnostics, find
Enter
out.
the actual running speed of the machine while you're collecting that sample.
That's right.
Okay, makes sense.
Subsynchronous. Subsynchronous is going to be anything that's less than turning speed. We're going to get into what faults we'll see here in a minute.
Okay.
And then we have non-synchronous. Non-synchronous is not synchronous.
Or asynchronous
Yeah,
is how
that's
some
right.
people use asynchronous.
That's right. That's right. So that's the peaks that are in between the turning speed harmonics. So, and those all tell you some type of issues too, and we're going to talk about that.
Okay.
So, subsynchronous. Subsynchronous can be another component in the machine that's maybe resonating, or it could be turning slower. You know, just like if you're taking readings on a motor that has a belt drive to a fan, the fan's turning slower, you may see subsynchronous frequencies on your motor
being induced from that fan that's turning at a lower speed.
That's correct.
Makes sense.
Another machine, like I was saying, belt drives, hydraulic instability, that would be like your oil whirl.
Yeah.
Oil wheel.
And that would typically be called more on proximity sensors, more online type
Yes. You'll see
protection
that.
monitoring systems.
Yeah. So rubs. You know, you may have a impeller on a shaft that's kind of loose and it touches off every so often, and rubbing. You'll see that at subsynchronous. Cage frequency. That's the fundamental train on the rolling element bearing. That one that is always subsynchronous, usually about 0.4 times running speed.
Oh, wow. That is significant.
Yeah. So synchronous is probably 93% of the issues that you're going to see out there in the world is going to be synchronous related. Unbalance or imbalance. Pitch line run out or eccentric shiv type setup that you might see, egg shape.
Okay.
Misalignment. Bed shaft. Looseness, mechanical looseness, you'll see all of it with harmonics, multiple harmonics. Blade and vane pass usually has to do with some type of flow issue. You know, a lot of your vane passes could be engineered that way.
Mm-hmm.
let's say you pulled a pump out that was pumping water, and now you're trying to put in an over here to pump gasoline, you're going to have all types of issues with it. So a lot of your blade or vane pass is when that individual impeller, and let's say you have 5 vanes, hit the cut water. And if your clearance is too wide or too tight, you could get some type of impact coming off.
Wow.
And it would be the number of vanes per rotation.
Okay.
So if you have 5 vanes, you'd see it at 5 times running speed.
Exactly. Makes sense.
Recip compressors, you have, single throw, double throw.
Sure.
You'll see that. Gears. Gear mesh is number of teeth times the turning speed of that gear.
Yeah.
So on motors, we could see rotor bars or stator slot issues. So synchronous is, like I said, about 93% of problems you can identify.
So if a machine doesn't have, I know you mentioned earlier being able to look at like a synchronous spike on some of the analyzers you use and be able to calculate a running speed. Do you typically go and install some sort of a temporary phase reference on that machine to capture that synchronous data?
Yeah, if you're going to get more into the analysis in that's what you'd want to do. You want to do some type of maybe order tracking.
Okay.
Or,
be like a magnetic pickup, or would it be like an optical sensor looking at a piece of tape? Or?
Yes, you could use numerous ways. If they have different types of tachometers that you can use out there that you actually could look at a keyway. Or if you can, like, run the machines down, put some type of reflected tape on there, use a photo tack or a laser tachometer that's out there. They have some of these strobe lights that you can actually look up and dial in the frequency too.
So if the machine can't be shut down, I guess that would be an instance where you would need to use something like a strobe light.
Yes.
Or something.
Yeah. The strobe, using a strobe light, they have one that designed for the vibration analysis, where you can go ahead and you tell it you want to track the 1X on it. It will track it, and that way you can do order tracking.
Okay, your synchronous analysis. Gotcha.
Yeah. So non-synchronous, again, could be another machine turning, an off frequency of some sort. Belt multiples. You get some type of belt resonance where the belts aren't tight enough and they're flopping back and forth. That could show up as non-synchronous, and multiples of it. What we see mostly in non-synchronous is rolling element bearings. All the different natural frequencies of the outer race, inner race, identified by the manufacturers. You're able to use that and locate if you have an outer race defect or you have an inner race defect. We're going to cover a little bit more on that. And you can use, if you don't know the rollers, you can use the number of rollers times RPM times 0.4 for outer race and 0.6 for inner race.
Okay.
And that gets you kind of close. That's kind of the rule of thumb calculation for calculating bearing.
Gotcha. So. And those typically on the bearing data sheet, a lot of times it'll have those fault frequencies on there for you, correct? Yeah,
you can go to a manufacturer of the bearing and get that information. You can also, people out there have databases.
Sure.
They'll have like every bearing known to mankind with all their frequencies in it too, that you can get. So, and there's also some places where you can go to. Most of them is transducer companies that they'll have some type of calculating type software that's on their website that you can use, where you can input all the bearing information. If you look at all the physical data of the bearing, and plug it in, and then it gives you your natural frequencies.
Oh, nice.
Inner race and outer race too. Yeah. So a lot of work doing it that way. It's a whole lot better just to call out, hey, what's the outer race?
Just get it that way.
Resonance is could be any type of natural frequency of a component in the machine. So it's what we call a system vibration. So it's has something to do with the system. It could be piping, it could be ductwork that's resonating in there that you're seeing in a non-synchronous to the machine rotation.
And it just seems like that could really become an issue on, like we talked about, variable speed machines earlier, machines that the load changes on, things like that, that can adjust that resonance.
Yes.
And affect, if you're operating that machine very close to one of its resonant frequencies for any extended period of time, your odds of a failure are much higher.
Absolutely.
So, yeah, I could see where that would.
Electrical anomalies will also show up non-synchronous, especially if you're looking at, let's say, a machine that's turning 3575 and you have a frequency of 7200 showing up, which is a 2 times line frequency. It's going to show up as non-synchronous peak.
Okay.
So it's good to know what all your frequencies are.
Sure.
Compressor surging, detonation. A lot of people say detonation. What's that? I think more like on a diesel engine or gas engine or something like that. Sliding surfaces like you'd have on your crossheads on reciprocating machines. Loop pumps. Loop pumps will have like a gear inside that I don't know what it is, but it's always at 11.5 times running speed.
Oh, really?
So or it might be 13.5 running speed, but it's always like a half order off of what turning speed actually is.
That's just from years of you seeing it.
Yeah, yeah. Centrifugal clutches, U-joints. Don't see U-joints on the cooling towers like you used to. That was like the thing that people would put. They'd have their drive shafts with U-joints just like a car.
I don't think I've seen one of those.
Yeah, that's old school.
Is it?
Yeah.
Maybe it's a 90-degree gearbox or something.
Right. That's the other thing. If you have U-joints, you got to make sure you have a 7-degree angle of some sort with it, so you get lubrication on your needle bearings inside. But you see them now, the U-joints, what we call our cardon shafts that you'll see like in Z drives on tugboats and work boats or something like that. There's also alignment procedures for that too. I'm going to talk about the difference between what is harmonics and what is orders. This gets confusing to a lot of people, because integer multiples of a given frequency is a harmonic, where integer multiples of turning speed is an order.
Okay.
So is an order a harmonic?
No, they're independent.
No, yes. If each order,
okay.
Yeah, each order is a harmonic, right? So
gotcha.
one order, one times turning speed, 2 times turning speed, 3 times they're harmonics, right?
Yep.
But what if we have a harmonic at 1.1? And then the next one's at 2.2.
Mm-hmm.
So it's, it may be non-synchronous. So it's not an order. It's just a multiples harmonic of a fixed frequency.
Gotcha.
So
see where those would get.
Yeah. So like you see you may see early stages of a outer race defect at maybe 10 times the outer race frequency.
Okay.
8 to 10 times, and maybe start seeing some sidebands with it too as it degrades. But that's like your early stages that you'd see of a variant. They'd be non-synchronous, but the harmonics would just be pretty much just harmonics of that fixed natural frequency.
Sure.
So where if you had vein pass and you had like 5 times, 10 times, 15 times, those are orders, but they're also harmonics too.
Makes sense.
So, yeah. So we see like we were talking about, this is 1x, 2x, 3x, integers of turning speed. And then we see the 1.1 and then an 8.3 and a 13.3 or 8.9 and a 13.3, those are all harmonics of the peak, but they're not synchronous. If you want to know how old this data is, just kind of look. I don't know if they can see my mouse, but August 2nd, 1989.
Okay.
So,
See your mouse here.
yeah, I keep all the data that I ever collect. So.
Yeah.
I got data.
You got a library of it.
I got data all the way back to 1987.
So when you go home at night, instead of turning on the TV, you just pull up some old data.
Yeah,
and
just
reminisce.
Yeah, that's right. But yeah, and if you look at the quality of the spectrum, that was, I think at the time we only we talk about lines of resolution, which gives you better looking spectrums, and
Sure.
I think we were only able to go to like 800 lines at the time.
That was a Cadillac at that time.
Yeah, that is. Now you can go out to 10,800, I think, lines of resolution. And keep in mind, the more lines of resolution, the longer it's going to take to collect that data too.
Collected process. Yeah. It makes sense.
So we want to, do our homework before we start a program. We want to go in and we want to look at the general layout of the machine. We got motor, gearbox, pump. We want to know what the components are. What's the shaft diameters? What type of bearings are in that machine, the operating frequencies. If we're going to build a database, we need to get all this information and built in for each machine.
Sure.
Then we can keep a history of it.
And this goes back to what we talked about earlier. I mean, once again, this data, getting all this entered correctly, loaded on the front end is critical because the output that you're getting from this will depend on these variables that you're entering in these early stages.
I mean, it's great to know if you have a variable drive on this machine or not. Especially waste. A lot of places are collecting data now. They're finding out. I'm not going to use a qualified analyst to go collect the data when I can get somebody else to collect it and use him to be more of an analyst in house.
Get the data to him.
Yeah. So, to make sure that guy's collecting good data, you want to make sure your whole program's set up right.
Absolutely.
So we look at motor, slip, slots, bars, we're looking at, number of blades or buckets on a turbine, vanes, coupling information. It'd really be nice to know if it was a Lovejoy coupling because it's 3 jaws, and if you start seeing 3X, maybe you have a misalignment.
That makes sense.
Belt data. Your belt frequencies, you need to know the center to center of the shaft to calculate your belt frequencies. Your pitch diameter, number of belts. You need to know your gear information. Your train layout. I mean, maybe you have 2 intermediates, first and second intermediate in the gearbox. I had an extruder gearbox one time I went into, and it had gears all over the place.
Everywhere. You know how y'all begin to do analysis on one of those.
Yeah.
Bearings and rotors and different speeds.
So that's, know the gear teeth, the number of teeth on each gear, and knowing the ratios. And, so what speed of each shaft that detect the what bearing problems you might have.
Yeah.
So, like I say, you got to know the RPM of what you're analyzing.
Sure.
So we just want to remember that when we collect our data, we want to be consistent. So some places they'll go in and they'll glue a washer. That's a cheap way. Use super glue, put a washer there, and then you can put your magnet on it each time. So you're collecting that data in the same place. Be consistent on your location each time for your horizontal, vertical, and axial. You have directional faults. Went out on a job one time and they thought they had an unbalanced issue and was collecting data in the horizontal. And the horizontal readings were running 0.15. The vertical readings were reading 1.5.
Wow.
So
Significant.
big difference in amplitude, really high. And it was all at 1x. Yeah. And then when went to look around to find out on this, it was what they did was they replaced a complete fan. So they pulled the old fan base and everything out, put another one in. They did it at night, and the night crew didn't anchor the bolts down for the fan.
So you had a vertical.
So you could actually go over there and with your hand spin it. And in vertical, it showed up, and I said, let's tighten this down. And once they tightened it down, then all the levels were around 0.15. Or less.
And that's a great example of, a lot of times you have the conversation of, if I put one sensor on this bearing,
Mm-hmm.
will it capture what I need? Well, it may or it may not. There's a lot of situations, just like you described, where the vibration is predominantly in one plane,
Mm-hmm.
and it's not hardly even detectable in the other plane.
That's right.
So that's just something to consider when you're installing systems, if you're debating, should I add that second horizontal sensor, or should I add that second vertical sensor? There's definitely times that.
And that's where the triaxial might work good for you.
Sure, exactly.
Like let's say you're mounting, you'd say, hey, I want to mount a probe on my gearbox and a cooling fan.
Yeah.
You can, normally mount one on the input side, horizontal, and it's based off people's budgets.
Yeah.
But, you can get a accelerometer with armor jacket cable, 20 feet long, for about $175, $200. So, if you wanted to put like 5 in there, you could, or you could get like and don't quote me on these prices. I'm just going off my head. I know, that's right. But you can get a triaxial for where it costs you, let's say $150 for each accelerometer. You can get a triaxial for like $400, maybe $350. That's somewhere around there. So you have only one cabling you have to worry about, with the triaxial and one sensor to put on there. So sometimes that works out better for them too.
Makes sense. And I would say probably if you're connecting the system to a protection system, a trip off line, you probably want to go with a single axis sensor in each plane, physically taking that measurement in that plane. If you're just pulling data to look at for analysis like we're discussing right now, a triaxial probably give you the majority of the information you need.
Yeah, a lot of your wireless systems are triaxial.
Yeah.
And they'll take X, Y, Z and temperature, and they'll take the velocity and acceleration. Some of them you can convert, and we'll also do displacement readings. Just depends on what you want to spend for your wireless system. It's all, you get the bare minimum on the bare minimum price, and then the higher dollar, you get the more accuracy and everything. 2 radials and an axial. Try to take at least 1 axial per shaft. Probe location is very important. We talk about where on let's say, electric motor that has a fan guard, you can't get it to the bearing, but where you really like to have your probe location is at the bearings themselves.
On the bearing cap.
Yeah, but you may have that much span of a fan guard from the bearing. But like I always tell everybody, it's better to take data here and not have any.
Yeah.
So maybe you find the bearing at its 3rd stage failure, because of the distance and that. You may not be able to catch it at 1st and 2nd stage, but at least you're getting something.
Sure.
Probe orientation is very important, especially if the guys are going out there and they're collecting data. You don't want to just get lazy and collect a horizontal at a 45-degree from top dead center. That's going to throw all your data off. No fan covers. You're tempted to do it, but that fan cover on the motor, it's going to be just like taking readings on a stereo speaker.
Yeah. Similar to your gearbox example earlier, that they were taking their reading in between the bearings or the shafts. So
that's correct.
A lot of flex between them.
So I put this no sheet metal and no fan covers because I was at a paper mill one time, and they had a and we're talking about this was in the late 90s, and they were having a big push for reliability. So they had all the paper mill operators come in and was going to give them a class on that. And somebody had mentioned that, hey, it'd be nice if we had like a little vibration pin that we could check. So they ended up buying a bunch of pins for operations. And part of their training was that you mark where you want to collect your data, to be consistent, right? Well, then the next week when we walked out there, they had like white paint pen circles on coupling guards, on fan guards and all that, and they were collecting data at those locations. And what they wanted to do was if they saw a problem, then they were going to call the vibration guys to come out. And we saw a very big problem here that they're going to be calling us all the time to come out. And then you walk out and go, it's a coupling guard. Why did you take vibration here?
Some great coupling guard vibration readings, but
that's right.
Very little bearing or
we got vibration here, but it's an alarm.
Yeah,
so,
makes sense.
Yeah. Transmission path. You want to get as close to the bearing as you can. Big, thick piece of metal there in a casing is going to be a little rough to get good data. Look around. Don't just be the robot out there collecting data. Just look at every machine, just kind of have some reference checks. So is there any leaks, or is there, a gauge broke on it or something like that?
Foundation cracking under the foot.
That's right.
Yeah. Like that.
So pay attention, care for, you want to, if there's grease all over the place, clean it up right there so you're not getting everything all on you. Foundation issues like we talked about. Structure problems. We may have a cracked brace of some sort. I've had that happen too, where went out to go balance something. It wasn't a balance problem. It was broke welds and cracked structure, Again, welds we talked about, and leaks, look around, see if you've got any leaks anywhere. Is your seal leaking? Make these notes. Instrumentation, what type of instrumentation does it have? Can I get pressures off this? Do I have some type of gauge on there that I can go back and look at the pressure of if I look at the data here? So kind of make that as a note on your database. Temperatures, pressures, flows. So we look at, when you're out there, I always love to go talk to the machinists or the millwrights, maintenance guys that are out there. They're the guys that are out there every day.
They know the nuances of that piece of equipment.
That's right, and I always take the Columbo approach, so you walk in and you talk to everybody and talk about, what's going on, how your vacation was and all that, and then just kind of easily slide into, oh, this machine over here, do you know anything about going on with that machine? And you'll be surprised, they're a world of knowledge when you get them in a relaxed area. You don't want to walk up and go, who messed this machine up or something.
Approach is everything.
That's right. Talk to the operators. They're out there every day. Again, you got to be constructive when you talk to them. Be a team player. Talk, you want to know the last thing done to that machine.
Sure.
We pulled the history up on one machine one time. The bearing was going out on it. It was a paper machine in the dryer section, and the bearing's about this tall. So you want to really be exact before you're going to pull that bearing. We went back and we pulled the history on it. It's been 26 years that bearing had been in.
Wow.
Yeah. So and it definitely had a defect. So once we pulled it, it had a cracked race.
Oh.
Inner race. So.
That's probably not a bearing you have a spare of sitting in a warehouse.
No, I don't have. Yeah, that's and the cost back then. I think they told me the bearing was like $35,000 now, and that was 25 years ago.
Oh, surely the price has gone down.
Yeah, that's. You wanted to look at the shaft, the coupling, the belts. Has anything been done to them? Have they been changed out? Looked at a machine last week that they had a gear coupling, and this machine never had a problem. And they decided we're going to change the gear coupling out and put in a shim pack flexible coupling. And once they did that, they started having issues with the motor looking for its magnetic center. And what they did, they didn't allow the flexibility for the mag center. So they actually had it pulled to one side.
It was fighting, the motor was fighting to get into its mag center.
Absolutely.
Okay, interesting.
So be prepared when you, if something's not broken and you fix it, be prepared to fix it again.
Yeah.
The history of the machine, general information on the machine, bearing clearances, changes that have been made. So alignment, very important to find out if the machine's been aligned. When was the alignment? How was the alignment? And then I always say, who did the alignment? So a lot of times, your people, you'll have like your really precision millwrights over here, and then maybe you have the guy that's transferred from Boilermaker, and now he's changed jobs as a millwright, and he's still, little tendency to still use the big hammer, or something like that. And so you wanted to kind of see if person needs a little help in training and alignment.
Sure.
But I put that there because I did have a steam turbine one time. Actually, it was called on unbalanced. The rotor had lost a couple of buckets in it. So it was, they pulled the cap off the turbine, pulled the rotor with the bearings out, sent it to a shop, got it all repaired, all balanced and everything. And they put the rotor back and came back a week later to look at it. It was running higher than it was when it had unbalanced. And what had happened was the shim packs, it had like a Series 71 Thomas flexible coupling. The shim packs had broke. And it had a expanded metal coupling guard on it, so you could take a strobe light, and when you strobed the coupling, it was just bolts to bolts. All the shims had cracked and come off, and so naturally we shut that machine down before it was getting ready to come apart. And being a steam turbine, it was going to overspeed.
Yeah.
Which the other story behind that, the trip valve spring had rusted off.
Oh, wow.
So it might have been a near miss with this. Yeah. So so I go back and I do my Columbo detective to try to analyze root cause, what caused all this. Talked to the millwrights. The millwrights told me we didn't align it. And this is a turbine wheel that turns 5,400 RPM. And it's like, why didn't you align it? Sure. They said we didn't have to. And I go, why is that? And this was in October. They said, we check alignment every April, and it was perfect in April. And I was asking him, I go, well, you broke the coupling, you pulled the rotor out. He says, yeah, but we never moved the feet of the case. So new policy, and this was like in the early 90s, too, when this was going on. So new policy now, we don't align at the feet, we align at the coupling, so. That was a big change in that, but just once we came back and put new element on there and opt-align lasers, and the beam went completely off. It was so far misaligned, and they just couldn't believe it. They go, we never moved the feet.
Yeah, how did it get it?
So that could have been a catastrophic failure.
That was a good catch.
Yeah. So then we look at, if the vibration is work related, is it something that we need to worry about? Do we have real problems? what is it? How bad is it? And then, see, I can't see that. Guess I can hit high right there. Oh.
There, put it down below. Let's see the screen over
There we
here.
go. There we go. Maintenance. Do we need maintenance for it? That's what I'm trying to. I'll let it catch up here.
Yeah. Catch up on your end.
Yeah.
Yeah, there you go. You're good.
All right. So yeah, do we have any maintenance going on? So all right. Issues as far as unbalance. You know, we have center mass, center of rotation, causes assembly errors, build up, probably one of the main causes for unbalance.
Yeah.
Wear, damage, broken, missing parts, voids in casting, and distortion. You know, maybe the fan blade is like, or like we have a squirrel cage that's bent and it's distorted on it, causing a heavy spot. Kind of what the data would look like. And again, here we're looking at data from November 1987. 1X was the same as it is, you know.
Didn't change, did it?
That's right. So we have pure 1X frequency is a good indication we have a misalignment. Kind of showing the difference between overhung rotor unbalance and center hung rotor.
Okay.
So shaft misalignment, we have angular, we have offset, when we have a combination. And then we also have like a bearing misalignment too. Let's say we have two pillar block bearings and one's cocked, it could give us a misalignment between the two bearings. We see what we're trying to achieve when we're doing misalignment. If we have angular misalignment, we'd be looking at 1x turning speed in the axial. Parallel is normally 2x turning speed in the radial. And it just really throws millwrights off when I tell them that you're misaligned side to side, but you're not misaligned angular. And then they come back and say, yeah, we were 22 thousandths off.
Wow.
So, you know, and how'd you know that? So well, the science told me.
How, I guess what percentage of the work you do is alignment work right now, Jack? Are you doing a lot of alignments or verification of alignments primarily? Or?
Yeah, a lot of times they'll call us to come in and verify alignment on machines out in the field. We come in using laser alignment tools, and we're able to set up, you know, lock the machine out, go follow safety protocols, and check the alignment. And just similar on one here recently that the alignment was actually, the machine was put back in service and aligned in, I think it was February, and this was in a really cold area of the world, you know. So when they did the alignment was, the temperature was like at 19 degrees. So they did a cold alignment there, and then it's, you know, we're in one of these places during the summertime, the temperature gets up to 105.
Yeah.
So it's 15 in the winter and 105 in the summer, and vibration levels increased as the temperature increased because of thermal expansion.
Sure.
So they thought they had an alignment issue, and they called me out to verify to see if that was, you know, the relationship of the thermal expansion of when it was cold aligned. So basically their next opportunity, they're going to do another alignment and try to do a hot alignment.
So in that case, were you both looking at the vibration data that you had to verify, yes, I have a misalignment, and then you were able to put your alignment tools on the machine and confirm it?
Yes, the axial vibration, which they actually had a online system monitoring the and it was case readings, but none of the radials were showing any type of high vibration. Everything looked kind of normal. Only the axial position was showing increase. And there, you know, if you looked at the trend, it was just trending up, and it finally went into a alarm.
So was that an axial vibration or an axial position that you were looking at?
It was a axial position, which was giving a deflection of the couple.
Okay.
So, but the other story on this is that the RPM was at 8,200 RPM.
Oh, wow.
So the higher the speed, you know, the sensitive of alignment.
Sure. Makes perfect sense.
So yeah.
Interesting.
So we have indications of what alignment will do. The top illustration is an operation deflection shape, which is a more advanced analysis that you can do on a machine.
The old, you're often referred to as the tail wagging on the dog.
That's right.
That's a pretty good example of what that looks like, why they use that analogy.
Mm-hmm. So we have two basic categories for mechanical looseness. We have the structure, could be base mounted split cases, bearing caps, bearing supports, and then we have rotating element type mechanical looseness, which impellers could be loose on the shaft. Fan blades, same thing, or fan hubs. Bearings could be loose in housing. Couplings, you know, shim packs coming apart, you know,
Sure.
Showing some type of mechanical looseness. Mechanical looseness is going to show up multiples of turning speed. So they're all going to be synchronous peaks and harmonics too. So that's how we can identify that, especially if you see something like this illustration here in the axial on a, let's say, motor pump. You see them in the axial, more than likely you may have some looseness coming from your coupling.
Interesting. So a lot of times when we think axial, just from the world I'm in, for machinery protection, you're thinking axial thrust.
Yes.
You know, or axial
you're
position.
Thinking more thrust.
You know, so that's something to recalibrate. When you're speaking axial, you're speaking axial vibration.
Yeah, I'm looking at the deflection more than anything.
And the data that you get from that. So that's interesting.
Here, kind of some illustration of what mechanical looseness might look like. Kind of over exaggerating, but
sure. Shows the effect of it.
Yeah. And we have rolling element bearings. We have harmonics at non-synchronous peaks, broadband energy humps, time domain impacting, and then early stages are going to be low amplitude, high frequency. With experience, an analyst can find races, you know, outer race, inner race problems, ball roller problems, cage, or what we call fundamental train, looseness in housing, excessive internal clearances, spinning on shaft, misaligned bearing, and lack of lubrication. Lubrication could be over or under. Causes of failures, 43% improper lubrication. All these stats came from, I want to say it was like in 2005. So
that's similar to the numbers I've seen. You know, and I think a lot of times people think, I'll just, you know, crank more grease into that greaser there.
Yeah.
But as you point out here, it's both over lubrication and under lubrication. You know?
So I'm seeing some issues now because of lubrication on bearings is that a lot of these facilities are using ultrasound to grease their bearings. You know, so they have like an ultrasound system, pump some grease, you can hear it, and lower it, and you've got the right amount of grease. But they're not following the OEM recommendations on how often, the frequencies you should do it. They get a little carried away and they go out there like 2 weeks later and do it again. Because they hear, you know, a little bit more sound to it, and they go, oh, I got to quiet it down, and they'll add a little more grease to it. And so with proper training, that works really good. But then in a lot of areas, they've kind of like the lacks of training from people handing off their duties to somebody else is where this is happening.
So the effect of under lubrication is pretty obvious. You run a bearing dry, you get heat buildup. You know, obviously you have the bearing fill.
Mm-hmm.
What is over lubrication? What is the
problem with over lubrication is that it causes more internal heat inside.
Okay.
And the hotter it gets, the fatigue the metal gets. So we had an incident like that one time that grease was coming out of the seals. They had over-greased and it bent the shaft right there at the bearing because of it. So it caused a failure.
That's because it has no way to dissipate that heat. It's basically holding that. You're making a hot spot basically there where the bearing is.
Right, and this was a new installation too. So basically, before they even started up, they just started pumping till
greased it up.
Yeah, a lot of these pillar block bearings, housings, and that has a plug in it, drain plug, and you can, because they can also use these with oil too. And but proper way to initially start a new bearing with grease is to pull that plug and pump grease in until you see grease there, and that way you're not pressurizing the housing full of grease, causing the pressure and the friction of everything of it inside to heat it up. This way you've got the right amount of lubrication in it, put the plug back on, ready to go. Mounting 27%, if they have one of these induction bearing heaters, it's great. They work great. But there's still people out there using a hammer and punch to kind of put the bearing on still too. So we see some of that issues.
So that's the installation of the bearing itself.
Yes.
Okay, gotcha.
Yeah.
So just those two things alone, the lubrication and the installation of the bearing is 70%.
Mm-hmm. And then 21% of manufacturer defects, already defected by the time you got it.
Yeah.
Could be that it was shipped wrong.
Sure.
I had a company in Odessa that they were building pumps and they were having bearing failures, and they asked me to come out and see if I could find out what was going on. First thing we did was cut one of the new bearings open and did an analysis on it, and we actually found some issues. But the biggest problem we found was that they were storing all their bearings upright next to a railroad tracks. That's so the where their storage room was with the bearings was like 20 yards next to railroad tracks, that a train would come through there 4 times a day at 55 miles an hour, and it would shake the whole building. So they were already damaging their bearings before they even put them on.
Wow.
And then 9–10% of normal life wear out. So that's kind of what we see. But like I say, this was all done back in the early 2000s. Now that we have more quality control going on, I'm sure we're getting maybe some longer life.
Sure.
Process has a lot to do with the bearing defects. If you're out there and you collect data and vibration shows it's running smooth, but somewhere in their process, when you're not collecting data out there, it goes through some type of anomaly, flow issue, and it jars it all the time, that could be killing your bearings too.
So you wouldn't even think about,
right.
Typically. So.
Yeah. Like we say, about 10% of bearings already have some type of defect on it already.
How they're stored, I could see where one being stored dry, developing rust, pitting, anything like that.
Yeah. So here's illustration of what bearing data will look like when you have defects on an inner or outer race. You can see the school of angelfish, which is well known in our industry, that if your time domain looks like a school of angelfish, you probably have a bad bearing.
That's interesting.
And,
It does look like.
Yeah, and that's the impacting. What you're seeing is you're seeing the ball rolling over a defect on the outer or inner race and impacting it, and it's ringing down. So it's like ringing a bell on that outer race.
Yeah.
And then it rings down. So that's why it
Starts
like
high and
one big spike, and
Yeah.
then
And now here, I see you, this spectrum here, you actually are looking at a full spectrum.
yeah. So, and then your frequency domain, you have what we call side bands from your fundamental peaks and your harmonics of that. And that tells us a lot too. You know, how far damage are we into? We have stage 1, stage 2, stage 3, or stage 4 failure of a bearing. If you're in stage 1, we always recommend maybe lubricate it a little bit and keep on monitoring. We get to stage 2, we look at it and say, yeah, it's still not ready to change out, but keep on monitoring it. And then when you get to stage 3, we tell our customers that, okay, we need to start planning. We know from case histories that a bearing at this speed will probably last 60 to 90 days. So we have some type of number to work off of. How long do we have? You know?
Sure.
And then we get to stage 4, we're rolling the dice.
Yeah.
We don't know when it's going to fail, but it's going to fail.
Running on borrowed time.
That's right.
Yeah. So stage 1 and stage 2, do you have kind of an estimate, or at those stages you're still, it's such a small defect at that point that you just kind of just keep monitoring it? I mean, it could be 1 month or it could be 1 year.
So it could be, it's all based off the RPM. So you could have one that you identified 9 months before.
Yeah.
And it's turning 900 RPM. Or if you have one turning 3,600, you may not get but 30 days out.
Sure,
You know,
makes
so.
sense.
And also we had issues one time. We had a bearing going out, and everybody thought it would be neat to grease the bearing. So operations was greasing the bearing, maintenance was greasing the bearings, the lubrication guys were greasing the bearings.
That's what it needed.
And you know, we had a bad bearing that on 1,800 RPM should have went 2 months, only went 2 weeks.
Oh, wow.
Because everybody was greasing it,
Yeah.
you know. So, and it killed it pretty quick. Here's some illustrations of some bearing problems. What bearing cause on the top left is Bernelli.
Yeah.
So on the top right is trash. You know, you had some type of trash in the oil or something that
Contaminant that was
yeah, contaminant. Bottom right is corrosion. And then bottom left is electrical. So just some illustrations, some indications that you can see.
So for someone that's new to diagnostics and looking at vibration data with the spectrums and with the FFTs and stuff, are you able to pinpoint you have an outer race defect or an inner race defect or a rolling element defect on that bearing?
Yes. A good analyst can actually tell you how long the defect is.
The size of it?
Yes.
Oh, wow.
Yeah, by analyzing the waveform.
Okay.
You know, you can stretch the waveform. It's time, you know, frequency. So knowing the RPM, how many times a roller's going over there, and the rate of ring of the impacting, you can calculate
the span of that.
Yeah, the span of it. So,
That's interesting.
yeah. So, and another cause that we see a lot is phosphorinelling. Phosphorinelling is where, that's for an example, you have 2 electric motors driving pumps, and they only run the A, they never run the B. But there's residual vibration coming through the base and everything. So the balls on this one are doing this, but it's great because you got lubrication there, right? Eventually, though, it pushes the grease out of the way, and it's metal to metal fatiguing.
Ah.
And you'll have like a perfect defect of where the
The
balls
rolling
were.
elements actually in the outer race.
Right.
Or I guess maybe even the inner race too.
And, you know, we recommend that they switch machines monthly, you know, part of reliability, you definitely want to know if both machines are operating right and will start up. We've had it where they'd switch over to a second machine and it wouldn't start because of something wrong in the substation. You do want to know what your machine's doing, and plus what this does too is it keeps your bearings lubricated from phosphorinelling.
Reminds me of, you leave a vehicle parked on concrete for any extended period of time, you'll get flat spots, on your
That's
tires.
right.
That sounds like similar.
That's right. And that's what happens is the phosphorinelling starts out and it's mainly a chug hole in a highway. And then once you start that machine up, then
shifts it away.
Yeah, it's just like tires going on a chug hole.
Yeah, makes sense.
Gearbox faults. We see our illustration of what a gear mesh with side bands look like. A lot of analysis we would use is our waveform. The waveform will show us impacting, and again, this is where you can go in and you can actually see, the size of the fault by using your waveform. It's a little more advanced analysis, that you get into. Here's some gear teeth failures. You can see one in the top left, they were having some type of arcing issue. It might have been when this was running that they were welding somewhere and it was welding through it.
So it was making contact through.
Yeah, the top right would some type of fatigue that was caused by lack of lubrication. Lubrication failed on it and chipped the teeth away. I think the one on the right bottom is similar to the one on the top. And then the one on the far left bottom is misalignment, gear misalignment.
Oh, wow.
So
that? Oh, yeah, you can see the additional teeth damage below. Gotcha.
Yeah, so a lot of ways to identify, looking at the failed components to see what was actually causing it to fail.
Sure. Yeah, because if you don't correct what the original problem was, you can put a new rotor in there and you're going to be in the same situation.
That's correct. So that's about it. That's what we covered. If there's any questions out there.
Yeah, I definitely appreciate that, Jack. I think it was a good intro for a lot of us, myself included. So yeah, guys, if y'all have any questions right now would be a good time to submit them. If there's anything we didn't cover, I'll leave the room open for a little bit for y'all to enter questions. Also, feel free to give us some feedback on these sessions. This is, I think, our second one to do like this, so we're all ears. Want to learn from them. Hopefully, you got some good information out of it. If you need to, or if you would like learning credit hours, looks like we went just about 2 hours here. I'll send my email address here on the side. Feel free to send me an email, and we'll get a certificate sent to you for the number of hours so that you can log them as continuing education credits. Don't see any questions yet. Kind of answered a lot of them along the way. But with that being said, Jack, did you want to briefly touch on some of the additional kind of services, the motion amplification, the different sorts of things we can do briefly? Yeah,
part of reliability, you have other tools besides vibration analysis like we were talking about. We have ultrasound, where we can not just only do leak detection, we can also do bearing detection with it and things like that. And that's a good way, cost saving for your plant. For instance, we went out and did a air leak survey. They had 3 air compressors that were running solid all the time. We went out and found several leaks in their unit, and they went and fixed it, and they were running 1 air compressor full speed, 1 half, and they were able to have 1 be shut down. So that's energy saving right there, cost saving. Thermal imaging, probably don't have to really explain thermal imaging, going in, looking at a electrical systems, and we were shooting boilers the other day for refractory brick problems that they had in it, and had identified some. You know, your oil analysis is always a good tool. You know, I always say you're using vibration like a EKG you would use on a person. Well, then you draw blood. Well, you draw oil to do the same thing and analyze to see what other issues you might have. We have, you know, balancing, field balancing, and laser alignment, shaft alignment. Those are corrective tools that really needed. If people aren't aware of field balancing, or what is also called in-stu balancing, we in-place balance machines. So if you have a fan that's out of balance and it's a big, large fan, the cost to pull that fan out and send it to a shop and have it balanced could be very expensive, where we could balance it at speed right in place. So attaching balance weights to it, that practice is used quite a bit in the industry. And then motion amplification. Motion amplification video is very unique, using a camera that we're actually doing video vibration analysis. And maybe next month we could have a series on it.
I'd love that.
You know,
go over to our process unit and actually do some live.
Yeah, actually, I was here last night. So
I'm sure you got some good footage.
Yeah, so we could actually do some live footage, show how everything works. But
sure.
The way motion amplification works is that your video has like 6 million pixels on it. Well, each pixel is an XY vibration transducer. So you've got 6 million XY vibration transducers that we're measuring the motion of each pixel, and then does an average over it. And you take, like, you know, you can zoom into like maybe a structure issue or maybe a piping issue.
Pipe strain or something like that. You can really kind of identify that.
Right. And the only issue with motion amplification is that we're restricted to 2,300 cycles, hertz, in as far as our F max.
Okay.
For it, our frequency max. So, but most of our vibration issues are going to be under 600 hertz. So, sure. And any high speed, it might be a problem. But the camera works great. It solves a lot of problems. It will find crack welds while the machine is running, and you see things that you can't see with the naked eye.
That's interesting. Yeah, we're definitely going to have to get that going. And obviously, you guys are also, y'all are licensed to provide the Mobius certification,
yes,
which we're going to do some classes upcoming here for Cat 1 and Cat 2 certification.
Yes, we're authorized Mobius business partners to do the category 1, 2, 3, and 4 Mobius ISO training. When you're doing vibration analysis training, you want to get something that's accredited by ISO, like the Mobius. There's only 2 other places out there besides Mobius, and that would be the Vibration Institute or Technical Associates of Sharp, which offer the accredited ISO.
Their version of the ISO. Yeah. So I guess one of the differences here, though, we actually have a running process unit here. So throughout the course, you can actually take students over
and do live training.
Yeah, and so we have ways to inject air in front of pumps to create cavitation and things like that as well. So
right, and what's unique of the Mobius is that we have simulators. So we can actually go in and simulate bearing faults, outer race, inner race. We can simulate misalignment. We can do all types of stuff. And we have interaction with the student. Yeah. The student has a clicker. He gets in there and he can actually click on answering questions. And
nice. Not just sitting there looking at a presentation and taking a test.
And most of our slides are 3-dimensional models that are animated. So it's not just a boring slideshow that you get. You might have seen some of the animation that I had on there, like the rotor turning with the probes on it and things like that. That's pretty similar of what our training classes.
Well, good deal. Well, certainly appreciate your time. Feel free to send me an email. Regarding the presentation, Diane, I see that the request here about sending out the presentation. Let me get back with you on that. We'll probably do, if we send it out, we'll have to put it in some PDF format or put it on our website. But let me confirm the best way to do that. But I have your question here. So with that being said, thank you for your time, and look forward to doing more of these with you guys going forward. Thank you.